So I'm Prashant, and I'll be presenting our paper. I will start with the background. Snow simulation is essential in computer graphics applications. In movies, in computer games, there are games now that are dealing in snow settings. And on the other hand, if you look at a number of SDKs that are dealing with physics, snow is missing in most of them. It's because it's computationally intensive, and it has properties that other materials do not have, like it can get compressed, it can melt. So for example, with fluid simulation, those things don't happen. So there has been some work, as I will discuss in a few moments, on snow simulation in computer graphics, but the focus has been accuracy. And our group has been working on accelerating snow simulation so that it could be used for real-time applications. So if I quickly sum up the work in the computer graphics community on snow simulation, the first paper was in SIGGRAPH 2013, the first prominent paper. And it was semi-Lagrangian, based on a semi-Lagrangian model. And then there was a paper in 2020, also in SIGGRAPH, that was based on an SPH model. Meanwhile, we have been also working on the DEM, or discrete element method, for snow simulation. We have this real-time particle-based snow simulation on the GPU, and an improvement of that paper that utilizes an iterative approach. There's much more work on snow and ice. If you would like to check out, you can look at this state-of-the-art report that was published in Meteor Graphics this year. On the other hand, if you look at adaptivity in computer graphics, it's a very well-known phenomena. Even in simulations, if you look at SPH simulations, for example, they are trying to have spatial adaptivity in a lot of works. On the other hand, if you look at snow, this work is only starting to warm up. So, for example, to propose data structures that can leverage GPU more efficiently, or to use regional time stepping in a grid-based framework, which is applying temporal only adaptation. So those kind of works have started to come up even for snow simulation. So our contribution in this method is that we are going to take this our iterative discrete element based solver, which is already very high performing solver for snow simulation. And we're going to apply spatial and temporal adaptivity to that simulator to accelerate it even further. And we are doing all this on the GPU. So most of the things that we do to accelerate this solver, because this base solver is also on GPU, we accelerate the solver also on the GPU. That includes merging and splitting and region determination. So to introduce you to the base iterative DEM solver, the way it proceeds is that it assumes that all particles begin as snow particles with air entrapped in them with a certain radius, and as the air is squeezed out of the snow particles, they become ice particles. So there's a concept of compression. And of course, there are normal and tangential forces that keep particles away to reduce the overlap between particles. And there's also something that's not in any of the other frameworks, that is bonds between particles, because bonds between snow particles are very important to capture the right behavior. So the idea here is that to put it all together in a loop and to solve in this iterative loop such that the constraints are respected and the overlap is as minimized as possible, because these particles don't interpenetrate in real life snow grains. So you have these two extremes of particles, and then you can have any particle that's in between these two. So which is determined by eta, or the radius of the particle, and one can interpolate quantities like Young modulus and cohesive strength based on these two extremes and depending on eta. So what do? We take the basic physics solver of the base iterative DEM solver, and then we identify regions that are spatially or temporally adaptive, and where we can get some benefit by applying spatial or temporal adaptivity. We compute this activity, we assign these regions those activities, and then we start with particle splitting and particle merging for spatial adaptivity. And at the end, we apply temporal adaptivity so that particles or regions that are not doing anything can be frozen. So one of the simplest ways to compute the activity in any simulation domain is to use the grid that already exists in the simulation domain. So here is an example. So there are these smallest particles on the which are red particles, and then these are the largest particles, which are the blue particles. So these particles pass on their activity to the parent grid cell, and then the grid cell decides on the activity by taking the most restrictive activity and then passes it back onto the bar containing particles. This way it can be done in a very efficient and parallel way. This is what we do as well to compute the activity. However, we need two different activities. One is spatial temporal. It is used by both spatial and temporal activity determination, and the other one is only temporal. So the idea behind spatial temporal is to identify visually significant regions that require a higher resolution of particles. On the other hand, temporal regions are those regions that are trying to figure out which regions are inactive, and we can get some benefit from there. And we use a fast marching method for activity propagation. So once we determine the spatial activity, we have to propagate it so that we are prepared to deal with it as something moves and we are not taken by surprise. So we are prepared for the activity. So for that we use fast marching method, and the frequency of activity computation is adjusted, which means that we do not compute these spatial temporal or temporal activities in every frame. We do that every few frames, maybe every 100 frames, and then apply the adaptivity and then do it again. So here is an example for merging. Once the spatial activity is determined using the spatial temporal activity that we just talked about in the previous slide, particles that are identified as smaller than decided activity are merged together. So here is an example. Those two red particles are decided to be merged together. So this requires that there is a search that is launched for every such particle, and this happens in parallel. So all the particles are put together in a buffer, and then a search is launched for all those particles to look for a similar particle in the vicinity to be merged. And we try to match the attributes of the particle as much as possible for this merging. So for example, the particle should not differ too much in velocity or in the state, and in the hierarchy. So it should be like the similar color of particles. And when these merging begins, we give a certain time for it to happen. That's called the interpolation process. So the merging happens slowly. The particles transfer mass to each other during these max iterations, like 100 frames, so that there's no instability in the simulation. And the final particle consists the attributes as fairly as possible. For example, temperature and mass, of course, is inherited by taking the sum of both the particles. Similarly, for splitting, once particles are identified which need to be split, for example, because they have an activity that's now they have a higher activity than they had before in the spatial region. So those particles are tagged for splitting. So you see that for that we create a virtual particle to start with. It's a virtual particle with zero mass, which is very close to the particle that's tagged to be split, also done in parallel with all the particles put in a buffer. So slowly this mass is transferred from the big particle to that small virtual particle, and this virtual particle is moved away during these max iterations, and all the attributes are also equally divided between those two particles, like mass. For that we need an extra global buffer, which we did not need in case of merging. And some other considerations have to be made, which are mentioned in the paper, like delaying collision. So here is a picture that shows why we cannot just split the particles in one moment. Why we have to do it slowly, because even if we split the particles in just one go, there is an overlap. There could be overlap between the neighboring particles that will make particles go everywhere and make the simulation unstable. After we have applied the spatial adaptivity by splitting and merging the spatial temporal regions, we come to the temporal only adaptivity. So as I said before, that we need an additional activity on the coarsen grid. So we compute activity on the grid, but we use a coarsen grid instead of the neighborhood search grid, because that way we can further reduce the overhead of activity computation. So regions like, as you see, there's a lot of region in this particular scene that is actually not moving at all. Those regions do not need to be updated every frame. We can completely skip all the computation basically there. So, but sometimes what happens is that there are particles that were tossed up in the sky and they have a velocity of 0 before the velocity becomes again finite and the particle falls back. So sometimes those particles could be identified as inactive by the spatial temporal activity. That's why we need one more activity, temporal activity, to mark those particles as active, even like when momentarily they appear inactive. So we just identify those particles and skip most of the physics. So for this conference, I know it's very important to talk a little bit about the parallel part for the GPU part. So the spatial and temporal optimizations are globally synchronized, which means that all the particles that have been tagged for merging and splitting, they all tag together and then they are split or merged, and then the next cycle of tagging for merging and splitting begins globally. The same goes with the temporal optimization. We have CUDA threads because we have implemented this using C++ and CUDA and GLSL. So in the CUDA threads, we have two kinds of threads. One is per particle thread, which means that every thread is given the responsibility to compute physics attributes for each particle. But sometimes when we are determining the activity for every grid cell, even those are that is done through threads, CUDA threads, and one thread is launched per grid cell. There are certain components, certain inexpensive components in our simulation that could not be completely parallelized. One of them is FFM, which is the marching method to determine the regions for the next frames. So we do it in a sequential way. And the other one is when for merging pairs are identified, sometimes it requires atomic operations for bookkeeping. So those two parts are not completely parallel, but we have verified in our experiments that they do not have a very high computational footprint. So about the results, we have tried our method on various scenes, and as you can see that the temporal method provides temporal only optimization provides anywhere between 1.18 to 1.4 times speed up. On the other hand, the spatial method can provide higher speed ups, especially with increasing number of particles. So we have tried it with 3 million particles on GPU. On the other hand, if we combine both the spatial and the temporal adaptation, we can get speed ups which are like 3.5 or above. So we hope that if we have more particles, 4 million, 5 million, we will get higher speed up. Before I show you the videos, also to bring this up here, that the kernel cost, the various kernel costs. So as we see that physics is still a very prominent part in terms of the CUDA kernels, the time spent on the CUDA kernels, and the overhead of the adaptive, whether it's spatial temporal or spatiotemporal, is not that high. It's very low rather. On the other hand, the GL buffers, the transfer of buffers, CPU GPU transfer is still is a very prominent part that could be taken care of in future implementations. So let me show you this video. So what you see here is the base simulation with 1.15 million particles, then the spatial only, temporal only, and spatiotemporal. And I show it here together, all of them together, so that it's easier to see that there are, the simulations do not look exactly similar. There is a difference. You see that in another scene where the speed up is about 3 times. So as a region is marked to be split or merged, there is some additional activity that's happening for merging and splitting, and that's why there are some extra what you call artifacts or unrequired or undesired activity in certain regions. But on the other hand, if you look at a number of computer games, especially that are dealing with snow as a mass, not like for some micro level interaction, this kind of activity might be tolerated. It might not be something that's kind of a very big deal. And here I kept this scene for the end to see that to show that if we have like the micro level interaction like with shoes, then this pronounced activity is the most noticeable because of merging and splitting. Although we do get a speed up, and if we zoom out, maybe it'll be more acceptable. So to sum up, we have presented our method that can provide speedups of more than 3.5 times in some cases with 3 million particles by applying spatial and temporal adaptation. The quality of base simulation and the temporal adaptation only are very similar. On the other hand, the spatial adaptation causes some, creates some additional effects which could be perhaps minimized in future work. It could also be that the discrete element forces are different in nature from SPH forces, smooth particle hydrodynamics forces, and they have smaller smoothing kernel. That's why these forces have probably a different nature, and that also needs to be incorporated into some future work. And finally, this CPU-GPU overhead could be a critical factor in some cases that could be minimized by trying it on Vulkan on DirectX 12. So thank you so much for your attention, and I'll be happy to answer your questions.
All right, we have time for maybe a couple of questions right here.
How inactive particles are identified?
So particles that do not move, which have like a zero velocity. And we keep identifying those particles every few frames and tag them. And then if they are going to get active again, we activate them using FFM, fast marching method.
What happens when two particles are supposed to merge, and then there is an event like collision with something, and then they move apart? Because your merging process takes like a few iterations. What happens if during the merge process, like the particles move apart?
But I have not been able to completely hear it out. Could you?
What happens when two particles that are supposed to merge move apart during the process?
So the question is that what happens if two particles that are supposed to merge move apart before merging happens, right? So if the physics is working in the fine way, the way it's supposed to work, the particles should not get that close to each other. Nor move so far away from each other during a small span of time after they are identified. They should move slowly, right? And that slow movement should be still make it traceable to identify which particles have been marked for split merging together. If particles move away that quickly, then there's something wrong that's happened. So this global iterative loop is actually making sure that any particles that have overlap, they are moved apart from each other in a synchronized manner globally. So all particles, there was a paper a long time back, it's called Predictive Corrective Incompressible SPH. So the idea is taken from there, but if we do it globally, we do not, it could be done together for all the particles and in a very efficient manner. So that's what we do.
Right here?
You obviously probably need some different visualization, but have you considered what would be the challenges of applying this method to like other materials, such as like transitions from like smoke to fire?
So what you're asking is about the transition from soft?
The applicability of your method to other materials.
Other materials. So the question is that what is the, how does it go for other materials for a similar method, yeah? So in the related work slide, we talked about many methods in computer graphics with SPH simulations. People have tried like the spatial adaptation a lot. One of my previous work has also tried temporal adaptation in SPH. So it seems that I think in every kind of method it has been tried. But because discrete element method is slightly new in computer graphics for snow simulation, it was not tried. So I'm pretty confident that it can work for 95% of the methods, And the only thing is that would it be parallel? And here in this case, if the base solver is parallel, we have been able to make it as parallel as possible, and that's why. So the base solver is the fastest existing snow simulator, and now you add up the speed up of 3.5 times here. So I think there are very high chances. That's my guess.
Okay, I think we have one more question over here to the right. Over here.
You mentioned that you guys were globally synchronized. What percent of the time are threads spent idling and waiting for the synchronization?
So the synchronization is happening when CUDA kernels are launched. So there's no extra overhead for synchronization. You just wait for the CUDA kernels to be finished as usual, like you do that in every frame. And but you know, the reason why I brought up that point was that you can have this splitting and merging, which is temporarily, or let's say in a certain region synchronized, not globally synchronized. But we do that in a globally synchronized manner, and it works very fine.
Great. Well, let's thank our speaker.
Thank you.